Hi YouTube viewers, it is Crystal here, and in this video what we're going to talk about is a split plot design, which is a type of experimental design. The split plot design is one of the most important designs applied in experiments when one factor is more challenging to randomize than another. So split plot designs allow researchers to study both factors effectively. So we're going to give you an example of a split plot design. Is an irrigation method is a whole plot times fertilizer type as a subplot on crop yield. So the null hypothesis is going to be no significant difference on crop yield, and the alternate hypothesis is going to be a significant difference on crop yield. Okay. And so in order to demonstrate this, we're going to review the code of a program written in R of a split plot design. So the first thing that we're going to do is we're going to set the seed. And the reason why you set the seed is so every time you run the program, the variables are going to be initialized to the same value. So you type set.seed brackets 1 to 3. And now we're going to simulate the whole plot factor, which is irrigation. So irrigation becomes factor brackets rep, that's a replicate, repetition vector, bracket C, which is a vector, which is drip and spray. And so each is going, 6 is going to be displayed 6 times, and spray is going to be displayed 6 times. So you're going to have 2 whole plot levels with 6 subplots each. And then your whole plot of your field is, so your field becomes factor, which is rep, that's a repetition vector of 1 to 4, each of 3. So you're going to have 4 fields, each split into 3 subplots. So you're going to have a subplot factor, which is fertilizer. So fert becomes factor, brackets rep, that's repetition, brackets C, which is a vector, F1, F2, F3, and it's going to be 4 times. And then you're going to calculate the true effects. So irrig effect becomes a vector of drip equals 20, spray equals 17. And then fertilizer effect becomes a vector of F1 equals 0, F2 equals 3, F3 equals 5. And then we're going to have the interaction. So F3 works especially well with drip irrigation. So your interaction effect is if else, brackets, irrigation equals drip, and fert equals F3, comma, 2, otherwise 0. Then we're going to do a random whole plot error. So that's field level. So whole error becomes R norm. That's a randomly sampled normal distribution of 4 samples with a standard deviation of 2. And the whole error expanded becomes rep, brackets, whole error, and each equals 3. So you're going to have 4 samples times 3 is 12. You're going to have random subplot error. Subplot error becomes R norm. That's a randomly sampled normal distribution, brackets 12, comma, standard deviation equals 1.5. You're going to have your response variable is yield becomes irrig effect, irrigation, plus fert effect, fert, plus interaction effect, plus whole error expanded, plus subplot error. And we're going to take all this data and we're going to put it into a data frame. So that becomes data.frame brackets field, comma, irrigation, comma, FERT, comma, yield. And then we're going to look at the data frame. So we're going to go down and we're going to find the data frame. So this is the data frame that we have created. So you've got 12 rows by 4 columns. So you've got your field is your first column, your irrigation is your second column, your FERT is your third column, and your yield is the mean, is the fourth column. And so you can see you've got 1 3 times, 2 3 times, 3 3 times, 4 3 times. And then you've got drip 6 times and spray 6 times. And then you have 1 2 3 4 times, and then you have the means of all of that. So that's the data frame that we have created. So now what we're going to do is we're going to do a split plot ANOVA. ANOVA is an analysis of variance, and in the R programming language, you have 2 types of ANOVA. The first type of ANOVA is what you use when you are hypothesis testing, and the second type of ANOVA is what you use when you have a linear regression model. So we're going to be using the ANOVA with the linear regression model. So AOV brackets yield. Yield is your dependent variable being y, and you've got a little tilde sign, and irrigation times FERT plus error brackets field irrigation. And so what that is that is your x variable or your independent variable, and data is dat. And then we're going to fit it, and then we're going to print off a summary of it. So this is what happens when we have fitted it. So you've got your irrigations and your residuals, and then you've got an error within. And then so it gives you your degree of freedom, your sum squares, your mean square, your F value, and your B value. So with the field, you have a p-value of 0.852. So with the field, it means that there's no significant difference. But with the within, you have a very low p-value, being one of them for the fertilizer is 0.0034. So in that instance, you would reject the null hypothesis in favor of the alternate hypothesis, meaning that there is a significant difference. And the irrigation fertilizer, you have your p-value is 0.322. So that's going to be higher than the significance level of 0.05. So you would go with the null hypothesis in that event. Okay, now what we're going to do is we're going to plot our calculations. So the interaction plot is interaction.plot brackets x.factor equals FERT, comma, trace.factor equals irrigation, comma, response equals yield. Color is a vector of steel blue and tomato. Line width is 2. Main is the title of the chart, being split pot design, irrigation times fertilizer. X-lab is the label on your x-axis, being the fertilizer. Y-lab is the label on the y-axis, meaning mean yield. And then you're going to have a subplot of the means plots. So T apply means becomes T apply brackets dat $ yield, comma, list brackets dat $ irrigation, comma, dat $ FERT, comma, mean. And then you're going to have a bar plot brackets T apply means, comma, beside equals true, comma, color equals a vector of steel blue and tomato, comma, main is the title, is treatment means by irrigation and fertilizer, and the label on the y-axis is yield, legend.text equals true, and args.legend equals list brackets title equals irrigation x equals top right. So we run the program, and this is what we come up with when we run the program. You've got a split plot design, irrigation times fertilizer. So you've got the mean yield, and so the type of the fertilizer determines the mean yield. So you've got three types of fertilizer, F1, F2, F3. It seems that F3 gives you the highest mean yield with both the drip and the spray. So that's it for this video. The next video is going to be on another statistical experimental design subject. So I hope that you decide to watch the next video, and I hope that you've got something out of this video. So I will be communicating with you soon in the next video.